Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to lecture number 5 for your course of communication technology. My name is Engineer Jaffar and I'm your instructor for this course. So the topic of today's discussion will be regarding the amplitude modulation. But before going into the topic, let's talk about that what we have covered in the last class. In the last class we have discussed about types of modulation and different techniques, or you can say different motivations for that we need to have this phenomenon of or this process of modulation. So the first type was amplitude modulation. In today's class we will be discussing regarding the amplitude modulation and how the signal is amplitude modulated, and then at the receiver end side how that signal is then in the receiving end side how the signal is again demodulated, and what is the efficiency of this technique. And in the last we will discuss about different bandwidth requirements of this amplitude modulation. So let's get started. So first of all, the thing is that what is actually this amplitude modulation. So let's say you have a source, and this is your you can say transmitting end side, or you can say this receiving end side, and this is your destination, or you can say the sink. And the first thing in the modulation is, as you know, that we basically superimpose a baseband signal with a small frequency m, and we superimpose it with the carrier signal. So this baseband signal is embedded into the modulator, and this modulator basically superimposes this low frequency signal on a high carrier frequency signal, and the signal is then sent into the channel, and the receiving end side the signal is again demodulated by giving the same carrier frequency as input, and that frequency is then superimposed on this incoming frequencies or incoming signals, and you get the original signals with the actual frequency of FM. So you get this kind of modulation and demodulation in the amplitude modulation or in any other modulation. So you see the thing is this is the diagram which will show you that this was your actual signal. It was then superimposed on a carrier signal, which made it something like this. You can see this is the amplitude modulated signal, and the signal of the frequency of this signal is basically increased. You can see that the frequency of the signal is increased, and it is again demodulated at the receiving end side, and you get the original signal back, which was the same as it was here. So how does this amplitude modulation basically occurs? In amplitude modulation, the amplitude of the high carrier signal is varied according to the instantaneous value or instantaneous amplitude of the modulating signal m of t. We have talked about m of t and d of t. For instance, let's say our signal is analog and we have denoted the signal message signal as m of t. So let's say that we have a model m of t as such as cos 2 pi fm t or cos omega mt. Omega is nothing but the angular frequency, which is replaced by 2 pi fm. So let's say this is your message signal or baseband signal, this m of t, and this is your carrier signal of high frequency, this cos 2 pi fct or cos omega ct. This is your carrier signal. Now if you basically superimpose both of these signals, it means that you are doing this kind of scenario. You are basically superimposing this thing, and you get the amplitude model signal s of t, that will be equal to ac plus m of t into cos 2 pi fct. So you just multiply both of these m of t and this carrier signal. Basically you are not multiplying, you are superimposing this signal. So this is the actual equation, and we will in the coming slides we will see that how this equation is derived. So don't worry about that. For instance, let's just say that it is the final equation, and there is the basically you can say that the combination this all of these information that we have just provided you. So in the amplitude modulation signal, we have to derive some equation, and let's talk about the mathematical expression for the AM in the time domain. So in the time domain, you can see that we have this signal A plus cos k cos omega mt into cos omega ct, and this was your message signal, as I've told you, and this was your carrier signal. This side was your carrier, and let's say this side was your basically the baseband signal. Now if you expand this equation, you will get cos omega ct plus k cos omega mt into cos omega ct. So you have multiplied, or you can say you have expanded this equation, the above equation, using this formula cos a into cos b. It gives you 1 by 2 cos a minus b plus cos a plus b. So if you expand this equation, you will get this equation will be termed as, or you can say expressed by this equation. So this is your final equation, but this is in the time domain. Now if you convert this into frequency domain, you will see that there are three terms actually. The first term is with no phase shift, that is on omega ct. So this is the first term, and there is a second term. You can see that this is the delayed version, and this is the other version, shifted version. These are two versions. So basically there are three you can say terms in this equation. The first one is a DC component, that is basically exactly at omega ct. So this is the carrier term, which I have highlighted for you. This is the second term, this is right here, and this is the shifted version or the delayed version, this is right here. So there are three terms providing you three different kind of outputs. But you can see that this is this is basically our carrier. When a is equal to 1, you will get, let's say this a is equal to 1. So this carrier will be, this will be the carrier signal, and this is the upper side band, and these are the lower side band. So you see that amplitude modulation basically provides you two copies rather than a single copy of modulation. So one will be the at the positive hand side, that is the upper side band, and the second will be on the negative hand side, or you can say the lower side band. So this is the you can say there are some pros and cons of this technique as well. We will discuss that in the coming slides, so be patient. So let's talk about the power consumption of this AM. So you can see that power consumed is a bit larger as compared to the other techniques that we will be studying in the coming lectures, because the reason behind this high power consumption is the dual copies of this same information. So you see that this is the same thing k square by 4, and this is the same thing k square by 4, and you are basically having two copies of both of same information. So you are and there is another power of this carrier. So the total power will be the power of consumed to send this, the power consumed to send this, and the power consumed to send this. So there will be three powers. So the power consumed to send this carrier will be equal to this a square, and the both of these upper sideband and lower sideband, upper sideband USB, and this is lower sideband LSB. So this upper and lower side bands also consume power for the transmitting, and the power is equal to k square by 4. So you will get, if the value of, let's say, a is equal to 1, so you will get the total power like something like this, 1 plus k square by 2. So this will be the total power of AM, and this will be much higher as compared to other techniques that we will be following in the coming lectures, inshallah. So let's combine what we have discussed till now. So the AM signal is generated using a multiplier, and all the information is carried in the amplitude of the carrier rather than frequency or phase. And amplitude modulation carrier signal has to be time varying envelope. So in the frequency domain, the AM wave form are on the lower hand side, that is this thing FM minus FC minus FM, and the upper sideband or USB will be on the right hand side, or you can say the FC plus FM. So let's come to the parameters that are used to define this amplitude modulation performances. So the first thing for any modulation is basically modulation index, or you can say mu or mi. So this modulation index is basically the percentage up to which you have or you want to modulate your signals. This is normally termed in the percentages, and this the decimal value for this ranges from 0 to 1. 1 means 100% and 0 means 0% modulation. So for any sinusoidal message signal, let's say m of t, let's say this m of t is equal to am cos 2 pi f mt, and any carrier signal, let's say this is your DC component of the carrier, cos 2 pi f ct. If you modulate these things, you will get this equation, and this modulation index is defined as the ratio between the amplitudes of the modulated signal and the carrier signal. So the ratio between the amplitudes of the modulating signal and the carrier signal, that is known as the modulation index, or you can call it K, or mostly it is defined as mu in the AM techniques. So modulation index K or mu is the measure of the extent to which a carrier voltage is varied by modulating the signal. So when K is 0, it means there is no modulation. You can see that there is no modulation. And when K is equal to 1, this means 100% modulation. And when K increases from 1, it means you have over modulated your signal. So there are three kinds of modulation indexes, that is starting from 0, then going above 0 and less than 1, and then greater than 1, which is over modulation signal. So let's talk about the index. When this index is equal to 1, so you can see that this will be your output. This will be the red is the upper sides, and this green will be the lower side of the waveform. And let's say you have basically decreased this modulation index, so you can see that there is not much difference in the amplitudes. Amplitude modulation is basically the variation in the signal according to the excuse me, according to the instantaneous values of the signal. So you can see there is not much difference in the upper sideband and lower side. There is not much variation in the upper as well as in the lower side bands. And when you comes that modulation index becomes greater than 0, greater than 1, so the amplitude is basically, you can see that it is called over modulated. This means that the signal will be overlapping each other at some point. So you can see that at this point the signal is overlapped, at this point the signal is overlapped, similarly at this point the signal is overlapped, and this is overlapped. So this is known as over modulation. There is a lot of difference between the ups and downs, and due to this this overlapping is caused. So this is known as over modulation. So let's talk about the modulation depth. So the modulation depth is basically the minimum peak to peak of waveform. There are two types of modulation that needs to be have there. The first one is the maximum, and the second one is the minimum. So maximum peak to peak waveform and minimum peak to peak waveform, and this may be equal to 2 AC plus 2 AM. So the maximum will be this is derivation of K, so you will getting AM by AC. So if you want to derive this equation, you can also do this for yourself. This value of K will be equal to AM by AC, and This is your waveform, and if you notice particularly this waveform, you will see that this will be constructing a envelope type of output or shape. So this is the envelope, and this thing is basically needful in the coming lectures for the demodulation side. So for instance, remember this for current scenario, just remember this term envelope, and we will be discussing this terminology in the coming lectures or in the coming slides as well. So what does a high percentage modulation is referred to? It is important to use as high percentage of modulation index as possible, but it is not very much of practical. You can say that it is not practically possible to have all the time this much of high percentage of modulation while ensuring that over modulation does not occur. So you want to increase your modulation percentage, but you do not want to have the over modulation, because when there will be over modulation, your signal will be a blurred type of you can say data information will be lost. So the sidebands contain the information and have maximum power at 100% modulation. So this is the usual equation, and we will be discussing we will be doing some kind of numericals in the coming class regarding this amplitude modulation, and you will be seeing over there that this formula will be of much use in that. So this PT is nothing but the total power transmitted. That is the you can see that there if you remember in the waveform, there was the one carrier and two sidebands. So this PT is the total power consumed, or you can say the transmitted power for the transmission of all these things, and PEC is just the carrier power. PC is just the power for the carrier. So PC is the carrier power and PT is the total power of the sidebands as well as the carrier. Remember this formula. This will be used in the coming lecture for the numerical portion of the AM or amplitude modulation. Let's talk about the demodulation of the AM signals. So in the demodulation, we have just the same techniques to take the signal back from the modulated signal. And in this type of process, we can use multiple techniques. The first one will be envelope or non-coherent detection or demodulation, and the second one is synchronized or coherent detection or demodulation. We will be discussing that in the coming slides. So you can see that this is your input that has just come that receiver has just received. So this is a type of envelope. You can see that this is an envelope, and in this envelope you have your information right inside of that. So you just passed it to a let's say this is a common filter, and you have passed your signal from common filter, and this is your output. So let's talk about the demodulation of using the envelope, or you can say a diode AM detector. So as I've mentioned you that this is your input signal, and using just a diode you can basically demodulate your signal, and you can get the actual signal back which was sent from the transmitting end side. Similarly, if your modulation index or depth is greater than 1, so you will see that there will be a distortion in the output of the demodulator, and you will be receiving a blur image of the information that was sent to you. So the other technique regarding this demodulation is basically known as synchronous and coherent demodulation, and it is much more similar to the modulation technique. In this type of modulation or demodulation, you basically the modulated signal that you have received on the receiving end side, you just multiply it with the local oscillator, the frequency of the local oscillator that is the same as the carrier signal, and you again apply the low pass filter and you get the actual output. We will discuss that in detail in the coming lectures. So here you can see that the derivation of how this coherent detection or demodulation occurs while assuming zero part delay between the modulator and the demodulator. So after solving, if you multiply your input with the local oscillator, and as I've told you that the local oscillator has to be of the same frequency that was there for the carrier, which was there at the carrier as a carrier frequency on the transmitting end side, you will multiply or convolve this whole equation, and if you solve this you will get this t. This VDC divided by 2 plus M of t divided by 2 means your message signal will be received as it was sent. This is the diagram of how this your actual information is working. So this was your basically message signal plus your d of t, VD of VDC, and if you do all this information that I've just provided to you, so this was your modulation side and this was your demodulation side. You again multiply the same frequency which was there for the transmitting end side. If you multiply this AM signal with the this local oscillator frequency, you will get the same output, but this output will be twice, or you can say the double of the output. So you will see that there is two outputs, and if you apply this filter, that is low pass filter, you will only get one output. So this was the coherent detection. So what is the difference between the diode detection and the coherent detection? So there are small differences between the diode and the coherent detection. In the diode, demodulator is basically unable to follow the fast modulation properly, whereas the coherent demodulator provides you a bit much efficiency of the demodulation. Similarly, the diode, the power is absorbed from the tuned circuit by the diode circuit, and in the diode, the distortion produced is not acceptable for some communications. But the only pro of this diode is basically it is very much of a simplicity, and the cost of this diode demodulator is very much low. So these are some pros and cons of the diode demodulator. When we talk about the coherent demodulator, the first pro of this coherent demodulation is basically the low distortion. The signal is less distorted as compared to the diode. The second pro of this coherent demodulation is that it provides you a greater ability to follow this fast modulation, which was not there in the diode demodulation. And the power gain of this coherent demodulation is also very much good. And the last thing, which is the con of this coherent, the only con of this coherent demodulation is basically the cost of this and the complexity level of this circuit. These are some pros and cons of diode and coherent demodulation circuits. I hope that you have understood quite a lot. Let's talk about the bandwidth requirement for this amplitude modulation. The bandwidth requirement will be in the amplitude modulation is a little bit high because of this double sideband scenario. So the total bandwidth required for any amplitude modulation signal can be determined by the bandwidth of the audio signal, that is 2B, or also known as BAM. That is the bandwidth of amplitude modulation will be the twice of the bandwidth that was of the message signal. So it will be as you can say that a bit more than as compared to any other techniques. We will be discussing and many other techniques in the coming lectures. That will be the you can say the derivatives of this AM, that will be the DSB, a double sideband with suppressed carrier, then single sideband with suppressed carrier, and in the last we will discuss about the VSB, that is vestigial sideband. So you will see that the bandwidth requirement for all those techniques will be less as compared to this bandwidth of the AM because of this double sideband. So this was all about your today's lecture. I hope that you have understood quite a lot from this session. I'll see you in the class. I highly recommend if you bring some good questions with you, because you know that the more you ask, the more you learn. Thank you very much. I'll see you in the class. Allah Hafiz.